We're going to be talking about some different kinds of functions. First, we're going to talk about what functions actually are, formally speaking. Then we're going to talk about injections, surjections, and bijections. Okay, so let's go ahead and get started. So a function f from a set A to set B assigns exactly one element of B to each element of A. Okay, so basically a function takes something in and it spits exactly one thing out. It's not like so like let's say that I plug in the value 2 into a function and I get out the value 5. So every single time I need to get out the value 5. It's not like sometimes I get the value 5, sometimes I get the value 8. That would not be a function. A function is something which takes in one thing and it spits out another thing. So the set of values that a function can take is called the domain of a function. Okay, so what it can take is called its input. So whatever you can put in, whatever you can input into the function is like the set of all those values is called the domain of the function. The set of possible values that the function can spit out is called the codomain of the function. The range of the function, alternatively called an image of the function, is the set of all actual output values produced by the function. Okay, so let's say I have a function, f of x is equal to x squared. This function takes a real number and it outputs a real number. Okay, so we would say that the range of the function, we would say that the domain of the function is the set of real numbers, and we would say that the codomain of the function right here is also the set of real numbers. But if you know anything about x squared, like when I take a number and I square it, I can't actually get a negative number. Like I can get 0 if it's 0, but otherwise it's going to be positive. Like I can get 0 if I plug in 0. Otherwise, I'm going to get something positive. So the range is actually the set of all non-negative numbers. Okay, so as we can see, like there's this concept of range and codomain, and there's actually a slight distinction, right? You can kind of think of the range as the smallest possible codomain. That's like another way you can think about it. Okay, now let's first talk about what an injection or an injective function is. Another name people often use for this is one-to-one. Sometimes you'll see this abbreviation one-to-one, like I might say like this function is one-to-one. Okay, so this is like a common abbreviation people use. So a function from a set A to set B is called an injection if for any two values, A1, A2, and A, if f of A1 is equal to f of 2, then I know for certain that A1 is equal to A2. Okay, so let's go ahead and look at this function right here. I have a function f. It takes some number from this set, 1, 2, 3, and it spits out a number. It maps to like something in this set, A, B, C, D. Okay, and they tell us exactly what this function is here. So f of 1 is equal to A, f of 2 is equal to B, and f of 3 is equal to C. So it turns out that this is an injection. This is an example of an injection. Why is that the case? So again, what's an injection, right? Whenever f of A1 is equal to f of A2, A1 must be equal to A2. So basically, if I have two values which map to A, that's a problem, right? Like two different values which map to A, that's a problem. Or if I have two different values which map to B, then also it's not an injection. But you can see, right, like every single value, like there's only one value which maps to A, there's only one value which maps to B, and there's only one value which maps to C. Okay, so this is an example of an injection. Now here's another example. Let's say I have this function g from the set of reals to the set of reals, and it's defined by g of x is equal to 2x plus 1. Okay, so let's assume that there are, and they tell us that this is an injection, but let's just kind of see this, right? So again, let's use the definition, very important. Let's say I have two numbers, x1 and x2, from the first set. So they're both from the set of real numbers. So now, based on this information, I can assume that g of x1 is equal to g of x2. What does this mean? This means like g of x1 is actually, like, I can plug in x1 into this like equation here. So I get that, like, basically I get g of x1 is 2x1 plus 1, and g of x2, I get that this is 2x2 plus 1. So pretty much, if I like, I can do a few steps, right? I can subtract 1 from both sides. This means that 2x1 is equal to 2x2. I can divide both sides by 2, and that eventually means that x1 is equal to x2. So what does this mean? This means that, okay, if the output values are the same, then the input values have to be the same. So that's just what an injective function is. That's what a one-to-one function is. If the output values are the same, then the input values must be the same. So let's go ahead and look at a few examples and see if these functions are injective or not. Okay, so is this function injective? So, okay, so let's just say that, suppose f of x1 is equal to f of x2. And I'm not going to write it, but obviously x1 and x2 are from the set of real numbers. Okay, so what does this mean? This means that 2x1 plus 3 is equal to 2x2 plus 3. Okay, so I can cancel some stuff out. This means that 2x1 is equal to 2x2. This means that x1 is equal to x2. Okay, so is it an injection? Is it a one-to-one function? Yes, because whenever the output values are equal, the input values have to be equal. Okay, so this is an injective function. All right, let's look at this one. Is this function injective? Okay, so I have the square root of x squared. So again, let's assume that, and if you want to really write this out in English, you can say, suppose g of x1 is equal to g of x2. So what this means is that x1 squared is equal to x2 squared. Okay, and now I can pretty much solve for this. I can get that x1 is equal to x2. But this is actually a mistake. X1 does not equal to x2. In fact, x1 actually equals to plus or minus x2. Now here's like some kind of way to see it, right? So like g of 3 is equal to 9. And g of negative 3 is also equal to 9. So based on the output value of 9, I can't tell you for sure what the input value is. So this function is not injective. Okay, if I have an injective function based on the output value, there's only one possible input value. But if the output value is 9, there's two possible input values. So this is not an injection. All right, let's look at this function. So I have something, it takes like something from this set, it outputs something in this set. Okay, so let's look. H of 1 is A, H of 2 is B, H of 3 is C. So for this output value of A, like I think only one maps to it, okay? For the output value of B, does anything else map to B? No. For C, does anything else map to C? No. Okay, so this one is an injection. All right, let's look at this one. Is this an injection? Okay, so the answer here is no, right? Because for the output value of A, 1 maps to it and 2 maps to it. So I can't like uniquely determine like what maps to it. So this is not an injection. So not an injection. All right, let's look at this one right here. So I have some function m from the set of reals to the set of reals, and they give us an equation for this function. M of x is equal to e to the power of x. Okay, so again, let's suppose that m of x1 is equal to m of x2. What this means is that e to the power of x1 is equal to e to the power of x2. Okay. Now, in order to solve this, this is like we can basically do this. We can take the natural log on both sides. So let's go ahead and say that ln of e to the power of x1 is equal to ln e to the power of x2. And if you know your log rules in general, like when I have log a to the power of b, this is equal to b times log of a. So I'm going to use that log rule. So this gives me that x1 ln of e is equal to x2 ln of e. But the natural log of e is just 1. So what this means is that x1 times 1 is equal to x2 times 1. So x1 is equal to x2. Okay, so this one right here is an injection. All right, so now let's talk about what a surjection is. So a function f is called a surjection, or onto. A function f is onto. It is surjective if for every output value, I can find something in my domain which maps to it. Okay, or in particular, for every element in my codomain, I can find something which maps to it in my input. Okay, so for example, let's look at this set here. So is there something which, let's look at this like function here. Is there something which maps to A? Well, yeah, like 1 maps to A, cool. Is there something which maps to B? Yeah, 2 maps to B and 3 maps to B. So this is a surjection because everything in the codomain, I can find something in my domain which maps to it. Okay, so if you want to use some formal language, or if you want to say it not formal, but if you want to say it in another way, this is a surjection because every element in the codomain has a pre-image in the domain. Okay. All right. So again, the pre-image, that's like another terminology. So I would say that the pre-image of A is basically the set with only one element, 1. The pre-image of B is a set containing 2 values, 2 and 3. Why? Because 2 and 3 map to B. All right, let's look at this one right here. So I have some function k, and they give us some equation. Okay, and this one is a surjection because for every value in the reals, I can find something which maps to it, because like there's always a solution to this equation. Like I can just say x is equal to the cube root of y. Now, one question you might have for me, right? Like, okay, let's say it's, yeah, this is fine, but let's say I have some function k of x, but this time the equation is x squared. So if you tell us that, like, okay, x squared is equal to y, right? So I pick some y value in here and I want to find x which maps to it, right? So can I just say that x is equal to the square root of y? Well, the issue here is that if y is negative, you can't do that, okay? I mean, yeah, you can have a complex number, or rather an imaginary number, map to this, but we're only dealing with real numbers in our domain, right? So this is no good. But this one is a surjection, okay? Like just this one right here with x cubed, it's a surjection because we can actually take cube roots. It doesn't matter if we have a negative number, we can still take the cube root. All right. Okay, this problem right here is actually the same one as what we discussed above. So I'll just let you maybe resolve it, but it is a surjection. This problem right here, we also talked about it. So this is not a surjection. Why is it not a surjection? Because this only maps to non-negative values. It doesn't map to negative values. All right, let's look at this one. Is the function h, which takes a real number, and it like outputs something inside of this interval, is that defined by okay, and if that's defined by h of x is equal to e to the x, is that a surjection? So let's see, right? So the thing, like the idea is we got to take something from here and we got to say there's something in here which maps to it. Okay, so I'll just say take, let's just say some y. It can be any y, right? Take some y in this interval. Okay, so the question is there something in here which maps to that y value? Okay, so in order to do that, we're going to try to solve e to the x is equal to y, right? So if we can solve it, that means we found our x value, we find something which maps to y. Okay, so let's say e to the x is equal to y. And we can't take the log or natural log of negative numbers, but we can take the natural log of positive numbers. That's no issue for us, right? So I can just take the natural log of both sides. Okay, so that means that x times the natural log of e is equal to the natural log of y, which means that this is just 1. This means that x is equal to the natural log of y. So what does this mean? I take, for any value in my codomain, if I call the value y, I can find a specific value, the natural log of that, which maps to it, okay? So yeah, this is a surjection. All right, next question. Is this function a surjection? Okay, I will let you think about this problem, but the answer is yes, it is a surjection. All right, this question right here, is it a surjection? Okay, can I find something which maps to A? Well, yeah, 1 maps to A. Can I find something which maps to B? Yeah, 2 and 3 map to B. So this is a surjection. So yes. All right, now we're going to talk about another very powerful class of functions. These are called bijections. And a bijection is basically a function which is both an injection and a surjection at the same time. Okay, so a bijection, you will call it like 1 to 1 and onto. Sometimes you'll see it like that. Another very popular term for bijections is a 1 to 1 correspondence. Okay, All right, so let's see this example right here. So the way I see if it's a bijection is if it's 1-to-1 and if it's onto. So this is 1-to-1 because there's only one value which maps to A. There's only one value which maps to B. There's only one value which maps to C. So it's 1-to-1. And it's onto because like for every value like A, B, and C, I can find something in this set which maps to it. Like something maps to A, like 1 maps to A, 2 maps to B, 3 maps to C. Okay, so it's 1-to-1 and onto. So it is a bijection. All right, this function n right here is a bijection. Okay, first of all, because for every value in here, something maps to it. So it's onto, it's a surjection. And if n of x1 is equal to n of x2, you can pretty much figure out that x1 has to equal to x2. So this one is also a bijection. So let's look at this. So is this a bijection? Okay, so there's two parts, right? We got to show, first of all, is it 1-to-1? Is it an injection? And is it onto? So let's first start with the 1-to-1. So assume f of x1 is equal to f of x2. So what this means is that 2x1 plus 1 is equal to 2x2 plus 1. So you can pretty much do some steps, but you'll pretty much figure out that x1 is equal to x2. Okay, so it is 1-to-1. Okay, let's look at onto. Let's pick like some y inside of here. Okay, and this in particular is the codomain. Okay, and then we can just try to solve and see if there's like some value of x which maps to it. Okay, so 2x plus 1 is equal to y. This means that 2x is equal to y minus 1. This means that x is equal to y minus 1 over 2. Okay, so in particular, you should like actually plug it back in. Like, you know what, I'll just do it, right? So if I do like 2 times y minus 1 over 2 plus 1, I'm going to get like y minus 1 plus 1, which is equal to y. Okay, so in particular, for any value y minus 1 over 2 maps to it. So it is onto as well. So is it a bijection? Well, it's 1-to-1 and it's onto. So it is a bijection. All right, let's go ahead and look at this problem. Is this a bijection? So we got to see, first of all, is it 1-to-1? And then we got to see if it is it onto. So first of all, is it 1-to-1? Well, I mean, it's not 1-to-1, and we talked about it earlier, but for example, notice that g of 3 is equal to g of negative 3. But 3 does not equal negative 3, obviously, okay? So it's not 1-to-1. And we don't even have to see at this point if it's onto or not, but it's actually not onto as well. But in any case, this is not a bijection. All right, this one right here, is this a bijection? Well, yeah, we talked about this example or like a very similar one. So this is a bijection. It's 1-to-1 and it's onto. Okay, is this a bijection? Well, it is onto because there's something which maps to A, something which maps to B, so it's onto. But it's not 1-to-1 because notice that 1 and 2 map to A, so it's not 1-to-1. Why? Because k of 1 is equal to k of 2, and obviously 1 does not equal to 2, so it's not an injection. It's not 1-to-1. Okay, so it's not injective. It is surjective, but that's not enough to be a bijection. So the answer is no. Okay, let's look at this one. Is this a bijection? So is it 1-to-1? Well, yeah, it is 1-to-1. I won't rewrite it, but we figured out that it is 1-to-1. Is it onto? Okay, so e to the power of something, right? That has to be positive, right? E to the power of e is a positive number, by the way. E is, and I should have told this earlier, but e is a positive number approximately equal to 2.718. And when I take a positive number and I raise it to an exponent, it's going to be positive. Like, it doesn't matter if the exponent is negative. It doesn't matter if the exponent's really small. It's going to be positive. So let's say I want to find something which maps to -1. I can't find it. So there is, so I'll just pick that. There's no value of x which makes e to the power of x is equal to -1. And you can also just notice that a -1 is in R, which is the codomain. So that means it's not onto. Okay, so this right here is not a bijection. All right, so that's going to be the end of the video. The concept of bijections in particular are useful for counting different things. So bijections are useful because they give us like two different ways to count the exact same thing. And sometimes like counting something one way will be quite hard, but if you can find a bijection, if you can prove that there's a bijection, sometimes you don't even have to prove it, right? But if you can just like know that there's a bijection, you can basically see that, okay, there's like an easier way to solve this problem. All right, so that's going to be the end of this video. I will see you in the next one.